Welcome to AI-driven perception, learning and mapping for drones. Today's lecture we will be talking about loss functions, different loss functions. In the previous lecture we talked about multilayer perceptron, learning algorithms, gradient descent, and then we talked about what will happen if the activation function, what will happen if the data is different, what will happen to the learning rate. We talked about how generalization is going to affect what is the relationship between learning rate, epoch, how many times we present the data, if the data is normalized, and all these aspects we discussed. This particular lecture focus more on loss functions, right? What we will cover in this particular lecture is we talk about multi-class classification problem, we formulate it, and then we talk about commonly used loss functions for a classification problems, and then we quickly represent what is optimal Bayesian classifier means and what are the factors that affects neural classifiers, and we discuss about how these loss functions are going to affect in terms of predicting the class labels accurately. Finally, we take an example, satellite image classification. We understand the effects of loss functions with respect to this problem and we discuss further, right? So one of the biggest aspect when we talk about classification is sample imbalance. See, when we talk about problem, multiple classes are there, right? So if you have 7 classes or 8 classes, data is going to affect the learnability aspects of it. But when we talk about data affecting the learnability aspects of it, we want data to be uniformly distributed in this space, which we really don't know what that input distribution looks like. When you have a multiple classes, how are they going to look like? In practical world, we will not have a data in all classes equally representing, right? And it may not represent the entire distribution space also. When you have this, how these loss functions are going to help us to learn the decision boundary as accurately as possible. That's what we are going to discuss in this particular lecture, right? Let's first formulate the multi-class classification problem, right? So we have our training samples. We represent that as a D. D is a set of training samples where X is the features which we are extracting from the sample and Y is the class label, right? And like this X1, X2, Xn, which means there are N samples are available for me to learn the relationship between this input feature space and the class label Y, right? So input feature, I am again defining it as an m-dimensional vector. Each X is an m-dimensional vector, right? The output for a neural network, see the class labels are always represented as 0, 1 or 2 or 3. These are integers, right? What happens is we cannot use this integer as it is, right? The class label, when I say class label, we talk about 1, 2, 3, 4 or 5. We are saying there are 5 classes. These are integers. But I don't want this class label to be represented as an integer. I want to convert the class label into some vector which I can you easily use to represent the output or the decision space, right? So what we call is a coded class label. When I say coded class label, right, this is Y will become a vector of dimension 5, right? Let's say the sample belongs to class 1, then the first output is 1, rest of them are -1, right? So this is my representation. If the sample belongs to the class, corresponding output is 1, other outputs are -1. So I can convert the class label 1, 2, 3, 4, 5 into corresponding coded class labels. The dimension of the coded class label is n, which means there are n distinct classes are present in the sample, right? Now if you look at the decision space, if the sample belongs to that particular class, the respective output is 1. If it does not belongs to the class, the respective output is -1, right? If I am just looking at in terms of probability, I can convert this 1 and minus 1 to 1 and 0. If I just simply add plus 1 divided by 2, then what will happen? Y plus 1 divided by 2 if I do. For this particular example, what do you get is 1, all these are 0. So what it says, the posterior probability of sample belongs to the class 1 is 1, whereas rest of the samples does not belongs to the class, their posterior probability should be equal to 0. Right? I can get some relationship between the output of the network to posterior probability here. What is my objective? Objective is to find the decision surface here. If you remember, when we talked about perceptron, we talked about simple logic gates like OR gate, AND gate and all that, where we are interested to find a decision line segregating these points, right? Because it's an m-dimensional vector, we want a decision surface and we want to approximate the decision surface or estimate the functional relationship between the input feature x and the coded class label y from the observation data. Here the observation data is nothing but your training sample, such that the performance is better. What is the performance here? Classification accuracy is better or maximized, right? If there are n samples, I want all the n samples are correctly classified. If all the n samples are correctly classified, my performance is 100%. Okay, so that my objective is you have to find a decision surface which is basically relating the input feature x and a class label y using the n data samples that what we have, that's observation samples, such that the neural network gives you maximum performance, classification performance, or all the samples are classified accurately. Now how do you find, because we converted the class label to coded class label, how do you find the class label back? Class labels are integers for us, right? So we just simply use argmax of yij. Here I am including two subscript I and j. I stands for the sample, the j stands for the output. Okay. So what happens is, I am looking at for j, for a given sample there are n outputs. Among the n outputs, whichever is the maximum and the corresponding argument is the class label. For example, let us say my predicted output y hat, right, is something like 0.9, 0.1, minus 0.5, minus 0.7, let us say minus 0.4. Now here if I use this particular equation, C is equal to argmax of j yij, now what I am looking at, if you look at in this vector, the maximum is 0.9, the corresponding argument is 1. So the class label for ith sample will be 1. That is how it is interpreted, right. Now what is that we are talking? We are talking of neural network as a classifier which approximate the relationship between x and y. Y is the true class label, right. So the neural network can be represented in this equation what you see here, f of w comma x, right. W is my parameters of the network, right. If you talk about multi-layer perceptron and assuming that there is only one single hidden layer, then there is a weight connecting the input layer and hidden layer, and there is a weight connecting the hidden layer and output layer. All those weights which we are going to update using the gradient descent, I am representing as a capital W. That is my tunable parameter. X is the input feature. When I approximate the relationship between x and y, I will have an error. There are two errors comes into picture, right, epsilon A and epsilon E. F is the function which trying to approximate. That's the decision surface that I'm trying to approximate, right? Epsilon A is nothing but approximation error. Epsilon E is an estimation error. Now we need to understand what will influence epsilon A and what will influence epsilon E. If I am out to talk about approximation error, is nothing but it is talking about the bias of the model, right? Even if you have a sufficient training data, for a given selected network, right, or given network, it may not represent the true decision boundary. Let's say we are talking about multi-layer perceptron and single hidden layer. The architecture, if I have to represent, right, number of input neurons are M. I talked about single hidden layer. Let's say there are L hidden neurons and N output neurons. In the previous lecture we talked about what will happen for a different activation function, what will happen for different initial conditions, right. Now this is my architecture. How do you choose L? If you choose L to too less, it affects the decision boundary approximation. If you put L too big, it will also affect the decision boundary, right. For a given network and given set of training data, right, it's very difficult to approximate the two decision boundary. There is always a gap between the best possible architecture and two underlying function, right. That's something which I am talking about model bias. What is the estimated variance? Given if the selected network is powerful enough, it's difficult to learn the best parameters, that finding the W, finding the true W, right. There are factors which will affect estimating these parameters. It could be the samples, or the samples may not represent the entire decision surface. You may have a noisy samples, you may have an imbalance in the data. When I say imbalance, what I meant is there are 5 classes. Let's say I have 100 samples. If I say imbalance is 0, what does it mean? All classes have equal representation. 20 samples from each classes. So the total 100 samples, right. Even though it is perfectly balanced data, the distribution may not be sufficient. The samples may not represent the true distribution. That's what I say, limited samples. I may need more samples to represent the entire distribution space, which I am not sure, right. That is another bigger problem. The data is an observation data. Your feature may be noisy. The moment the feature becomes noisy, it's very difficult to approximate the relationship, right. So these factors do affect your variance. The bias and variance is the biggest key one need to find, minimize it such that my approximated decision surface is as close as possible to true decision surface, which we don't know. Now in a summary, if I want to put whatever we discussed, right, I assume that there exists optimal neural classifier. I'm sorry, it's not visible here, which is nothing but there is F star corresponding W star X. I am assuming that it exists, right. I am assuming that, let's say if there is a single hidden layer itself is good enough, M L star right, M L star N. Assume that there is somebody has given me the information, this much hidden neurons are good enough, this L star is known to me, then I have the architecture. And choice of right activation functions also is given to me. Then the W star somehow I can find out, that's an optimal weight. Then we can approximate the relationship very well, and that is my true function. I am assuming that this true function exists. Because I don't know, I have to select a model. What I am going to do? I am going to choose a model M, L plus is my model, right? This is my model. Let's say L star may be 100 neurons. I picked up 120 neurons is my model, or 90 neurons as my model, right? Here again, I assume somehow I can find out true weight, right? If I know the true weight, then what is my classifier gives me for a given model? This is a function I can get. I may not get the true optimal weight. You know what are the factors affects, right? How you present the data during the training process. The loss function also is going to make us effect. Learning rate, momentum, all this will take you to either local minima. Finding a global minima is a bigger problem because the error surface is not going to be smooth, right? So finding W star even for a given L plus is very difficult. So estimated model is your f of W comma x. What is my approximation error? This is a true function. Somehow I know the difference between the true function and the f of W star x. If I talk about estimation error, is nothing but for a given model, what is that local minima I can get, corresponding W, right? The difference between that. That's my estimation error, right? So I have this with me. Approximation error, basically what we are talking of here, right? If you are looking at approximation error, what does that it really means? Can the architecture express the true function well? What are the causes? A model capacity may be low. If the capacity is low, I cannot learn all the variations in the data. So you have to play with the model capacity, which means you have to play with L star, number of neurons, right? You may have to vary the model capacity to C. If I have to mathematically define the error is minimization of W, expectation of x comma y, loss function which has with respect to optimal W that we wanted to get, right? The true decision function, right? If I look at estimation error, how far is the trained model from the selected model? It basically what's your weight? Is the local minima is far away from a global minima? Now if you look at what are the factors it affects, training data itself will affect. You may have a overfitting. If you learn it too longer time, you may fit with respect to your data. You may overfit, sometimes you may underfit. Generalization is the biggest challenge. We talked about what are the factors affecting generalization in the previous lecture. Sample imbalance, how the sample distributions are. All these are going to affect finding the optimal W. Now if I have to mathematically define my error, it is the difference between the function that I am, the estimated model and the true function is what is my estimation error. Now let's look at what are the loss function which is commonly used in the literature. We use squared loss, right? What we call least square. The difference between true y, let's say here D is the true data and y is my network output, y minus D the whole square. Then people just see that that makes sense if you are trying to approximate, but when it comes to classification, what does it mean y is more than 1? Let's say I just give a scenario. I ask a question, is this a sample belongs to apple? And I am showing an apple to you. And you say yes. Then I ask, how confident are you? The probability of this sample belongs to yes is, you are saying 200%. What does 200% means? Anything more than 100% is 100% only, right? You cannot have a probability having more than 1. Suppose if the network says I am confident that 200% confidence that this sample belongs to class 1, if I use a least square it will penalize for overconfidence. The modified least square on the other hand, it just allows, right? If y is greater than 1, it's still fine. Or y is less than -1 when you are expecting -1 as a target value, it's still fine. So the function sees max of 0, 1 minus yd the whole square. Right? So it's basically what happens if I want a d is equal to 1 and you are predicting, let's say 2. 2 into 1 is 2. 1 minus 2 is -1. Max of 0, -1 is 0 and 0 square. So you are not penalizing for being overconfident. Right? The other way to do, right, I want 1 but you are predicting -2. You are saying that this is not an apple. I am 200% confident it is not an apple, then I might have to penalize. How do I do it? Now one way I can use is I can go for 4th power, right, y minus d whole power 4. There is also another loss function which is commonly used in the literature. The most common used loss function is cross entropy. I am showing it here for binary cross entropy, but it is applicable for multi-classes also, right. So 1 plus d by 2, d is the true label, log of 1 plus y by 2 plus 1 minus d by 2 log of 1 minus y by 2, right. So I can use the cross entropy also to find the true classifier or true function, right, or estimate the true function or approximate the decision surface for a given training data and a model. I can use any one of the 4 loss functions and I can use a gradient again with these loss functions and update my weight, right. There are special loss functions are available. What I show is a binary cross entropy. I can do it for categorical cross entropy if you have multi-class problems, right. Every category I can just put an entropy and then sum it over and that becomes categorical cross entropy. I can use a focal loss. The focal loss is nothing but 1 minus y by 2, which is basically y is a predicted output, power gamma log of 1 plus y by 2, right. Here if you see I am not using the true value, I am trying to maximize the prediction, right. I can use a focal loss or I can go with risk sensitive hinge loss function. For a different portion of error, the losses are different. For example, if you look at the previous case where we talked about modified least square and cross entropy, both modified least square and cross entropy does not penalize the network when the value, let's say predicted value and the estimated values are greater than 1. Let's say I want this sample is not belongs to apple, I want -1. If you are saying -2, -1 times -2 which is +2 which is greater than 1, so the loss is 0. I am not going to penalize if your class is correct but your confidence is more. Anything more than 100% is 100% confidence, right. That is how it treats. Then it look at if a classification is correct but you are not confident, it uses almost like a least square error. But your classification is incorrect, right, but your confidence towards a negative class, then I have to penalize you with risk. The risk factor comes into picture or a scaling factor comes into picture. You are overconfident on the negative class, whereas I want a positive class, right. So if misclassification really happens and the confidence level for you is higher where it should be lower, so I will penalize it in squared term of weight. This is a risk sensitive hinge loss function. There is a hinging at different point, the loss surfaces are different at a different point, helps you to approximate the network, right? Here I can have a fixed weight. The m can be fixed a priori, or you can estimate the m based on your learning process. Then it is called adaptive risk sensitive hinge loss function. Okay. So these are quite commonly used loss function. What we saw the previous 4 are commonly used. These are very special loss functions, right? Now let's try to understand how these loss functions are going to behave. If you remember, we talked about ideal function, right? I'm talking about optimal Bayesian classifier. That's the Bayesian classifier. I know the true model, and somehow I am estimating the parameter, and that's my Bayesian classifier, which is L beta, right? Your network loss Rn will always greater than or equal to L beta. You can never be less than optimal Bayesian classifier, which is ideal classifier, which I can get. Plus you will have an approximation error, you will also have estimation error. Now I am not going to prove what is going to happen with this particular loss function, but it's very important. Someone going to use this loss function, you need to understand what is going to be its effect. The class labels are assigned to output when it is maximum. Selecting activation function also you have to be careful, right? If you look at a sigmoidal activation function, it saturates when Wx is higher. The outputs are between, if say bipolar sigmoidal, we are looking in -1 to 1. So towards 1, the Wx gets saturated. So it is very sensitive to noise in the data labels, right? It's sensitive to data also. The finite data, if the data is not distributed very well, the loss function is also going to affect. There is an imbalance in data. One class has more represented, the other classes are less represented. The network, the gradient will try towards the class which is overrepresented. You may have overfitting problem here, right? Generalization get affected significantly. If you have a larger sample, you will have overfitting problem. Generalization will get affected again, right? You cannot guarantee that least square will take you to optimal Bayesian classifier. Suppose you have well separated data set, right? There is a perfect separation is possible, and the data distribution is also covering the input space. Then there is a possibility the least square can get closer to optimal Bayesian classifier. But we cannot guarantee this in real world, right? Getting a finite infinite data which is representing the entire distribution is a bigger problem. For example, it's like if I'm doing a medical problem and trying to find out the cancer, it's like saying that give me more cancer data. Getting more cancer data is not possible, right? So you will have more normal than very few cancer samples. That kind of problems will be there. Now let's look at the modified least square. The difference between the least square and modified least square you don't penalize when y into d is greater than 1. So if you use subgradient, it increases the computational cost, right? The cost for gradient here, because you have that function, right, if condition comes into picture. So one can do output layer should have a linear activation function. If you put an sigmoidal activation function, you can never get more than 1, right? You have to put a linear activation function. If you put a linear activation function, you have to use a truncated output for loss computation, right, or the posterior computation. It estimates the posterior better. If you look at a convergence analysis and all that, I am just giving inference of that. For the scope of the course, convergence analysis is not required, but we have to understand the effect of this loss function. It may estimate the posterior better than d square, but it is not sensitive to data, but it's sensitive to class overlap. Like least square, this is also a problem. If there is a classes are overlapping with each other, both least square and modified least square cannot handle it. It's sensitive to, similar to least square, it's also sensitive to finite data distribution, imbalance in the data set, right? If you have more samples, overfitting problem also will come into picture. Generalization is an issue. So one way to overcome, like we discussed in the previous lecture, you may have to add in a momentum term. If you add a momentum term, it increases the computational cost of the gradient. So you have to understand, the balance between the computational cost for training versus the advantage what we are going to get by adding these terms, right? Now we go to fourth power, y minus d whole power 4, right? What happens? If you misclassify, it penalizes significantly. For a small error with the data feature space could be noisy, small noisy sample, you get affected significantly. But the gradient also vanishes. If you are coming closer to the true value, right, I want 1, you are predicting 0.9, the error is 0.1, 0.1 power 4 is a very small value, which when you are propagating through multiple layer, you may have a vanishing gradient problem. It may not update the weight. If I look at how does the posterior probability, estimation of that posterior probability, it is not better when compared to modified least square, right? It may be comparable with the least square, right? But it's not better than modified least square. Similar to least square, it's not sensitive to data label, but gradient stability is an issue. Sensitive to finite data, data imbalances, all these are going to affect my performance of the network. Again, overfitting problem will be there. You may have to add a momentum term or other factors we talked about in the previous lectures. One may have to consider to get a better generalization performance. Cross entropy. It gives a consistent towards optimal Bayesian classifier, right? But the convergence is slow. Others, least square will converge faster, but it's very slow. You need more time to learn. It estimates the probability better than modified least square, but it's not sensitive, similar to modified least square, and least square is not sensitive to data label. It handles to some extent overlap, okay, but it's sensitive to finite data, it's sensitive to data imbalances. Again, large number of samples can lead to overfitting problem. One have to bring in regularization methods or momentum terms to improve the generalization ability. Focal loss. It will also be consistent, but convergence again is slow. It estimates the posterior better than modified least square. It handles overlap better when compared to cross entropy. It handles data imbalance between classes effectively. The advantage of focal loss is overlap and sample imbalance can be handled better, but it is very sensitive to noisy label when compared to cross entropy. Of course, finite samples, finite data is a bigger problem, right? More samples, overfitting will also come into picture. But very important here is, by bringing focal loss, I can handle class overlap. I can handle to some extent of sample imbalance. When you are talking about problems where the tail is small, fewer samples are there for a specific class, you may have to consider using focal loss. Now, if you look at a risk-sensitive hinge loss function, it is also consistent towards optimal Bayesian classifier. but its convergence is slow because computation is heavy. You have various subgradients for different conditions, right? It estimates the posterior better than modify least square. It's not sensitive to data labels, handles class overlap better than the focal loss. Here M, if you make it adaptive, it will be better than the focal loss. It's not sensitive to the finite data and data imbalance. It handles the data imbalance effectively. If you use adaptive risk, it converges much better. But then it adds additional risk of how do we adapt the risk factors based on the estimation, which means it increases the computational cost. Right? Now, we talked about various loss functions, right? What we saw, the common issues when we are talking about learning. One of the biggest problem is generalization ability, right? Am I learning, am I fitting my surface, or overfitting my surface, or if I'm underfitting my decision surface? That's one issue. That also requires the observation samples representing the entire distribution properly. That we cannot guarantee. And we can also not get more samples from a specific class, right? Some of the classes could be underrepresented. It's not possible to get more samples. You may have the same samples repeated, but that's not going to add any new information to me. Right? Just because I want 100 samples from a cancer data, you cannot put 100 same samples because it's not going to add any new information. Right? It's not 100 samples from the distribution of the cancer class. Okay? So remember that sample imbalance is not just adding more similar samples, right? More same samples. I need from the distribution. That is not possible. That will also affect. There may be similarity between classes. For example, in the satellite image classification, I took this example to explain better. What you see, A, is the spectral image, right? Hyperspectral image. Every pixel has not just only RGB, it also has spectral data. Now, what I am trying to do, every pixel I am trying to assign to a specific class. It's something similar to segmentation, right? Every pixel I am assigning to the class. This particular image is in Karnataka region. It's a Kaveri belt data that I am just showing here. Now, what are we seeing? It's some part of it is a forest, some part of it is an agriculture land, some part is a barren ground, right? Some of these are shadow when I take a satellite image, right? So what we do, we go to ground with GPS, right? We just check. We can't do the entire region, right? We sample some few spaces and say, okay, this region, okay, I can see a tree. This tree is a pine tree. Again, pine tree has variations. Here we are showing 3 different variations of the pine tree. And this is a water body. This is agriculture land, right? So this is a barren land, there is nothing there. Here you have grass. There are urban settlement in this region, I am just marking it there. So every pixel in the satellite image I am corresponding to a specific classes, right? This is the data that I have. Now I have to get more samples. What will I do? I want more barren land. I cannot make this space barren land and collect the data, right? Variations in barren land with respect to spectral information is what we are looking at, right? I cannot get that. Whatever we have is the data, right? Now what is our objective? Given this finite samples where I can physically go, see what type of land it is and mark it, and the corresponding pixel has a ground truth, right? I have some understanding of the spectral information. With that also I can just increase the ground truth here. But it could be noisy, right? There could be a noise in my measurement too. Now what I am trying to talk here is, look at this particular example. I have a finite data. I don't have a complete representation of distribution of the specific classes, right? And also have a problem of noise in the data labels, or could be in my feature space. There is a possibility. There may be a small cloud. We do cloud correction and everything, but still that particular data is noisy. Feature could be noisy, right? So I have all the problem we talked about. Finite samples, not representing well the entire distribution, right? Certain classes are not represented very well, and noise in class label as well as noise in feature space. This is the best set I can use, right? What I did, I picked up 1000 samples from every class. Which 1000 is the right 1000? I have no idea. Close to about 1 million samples were there. I picked up 1000 samples from each class. How do I say that that particular set is representing it? For a different 1000 samples, my performance will be different, right? I somehow managed to get 1000 samples from each class, and I fixed the architecture, I trained the network. Now when I talk about it, architectures, you see when the loss function changes, there is a true function which is always be fixed model, right? For a different loss functions, different number of, I decided to go ahead with a single hidden layer, right? Single hidden layer architecture, right? For every loss function, the number of neurons in the layers are different. I am trying to optimize. I am trying to do the optimization. Okay, let me try with 15 neurons, 20 neurons, 25 neurons. I look at the validation performances. Based on that, I try to see which architecture come closer to my optimal. But you see here, again, each loss leads to this. The choice of loss function also going to affect, right? Now look at the performance. There are two metrics I am looking at. One is eta O, what we call overall accuracy, right? What does mean overall here? There are 3, 4, 5, 6, 7, 8, 9 classes, right? Out of 9,000 samples, how many samples are correctly classified, right? That's number of samples correctly classified divided by total number of samples is my overall accuracy. We talked about it in the previous lecture, right? What is average accuracy? For each class, how many samples are correctly classified, right? I compute for individual classes, and average of that is my class average accuracy. Now I am trying to look at it. Is the performance better in both in overall sense or individual class sense, right? So I tried with different losses what we talked about, and I summarized here. Now what I did one step further, instead of keeping the data samples balanced, I started taking one of the class, started reducing the number of samples in the class. It was 1000 samples, right? This is the performance we got. And one class, the class C2, right? That's a class C2. I started reducing from 1000 to 900, 800, 700, all the way to 300. Now what's going to happen to the performance, right? When up to certain, let's say up to 900, if you see, more or less all the networks, all the loss functions are able to handle it. Beyond that, when you start reducing, the performance started decaying, right? If you look at even the hinge loss functions, up to 600 is still able to manage. But if you don't have good data representation, the performance started decaying. The only difference is rate at which decaying is lesser when compared to least square. That's all, right? The drop in performance started observing for this. So sample imbalance is also going to be a biggest factor. in a real world data, we cannot guarantee any of this, right? That's a message I wanted to pass on. In a summary, we talked about different loss functions. We defined mathematically what is a multi-class problem. We talked about different errors, the model and variance, model bias and variance, right? Optimal Bayesian, suppose if a true model exists, true optimal weight exists, then that's the one which can approximate the relationship between x and y, that's the decision surface, that's optimal decision surface. What are the factors affecting the model bias? What are the factors affecting model variance? We talked about how we have to pick the loss function. We defined commonly used loss function and special loss functions. We talked about how these special loss functions can handle the overlap between the classes or sample imbalance, how they help in approximate the posterior effectively, right? We talked about special loss functions, why they are important, like a focal loss or risk sensitive hinge loss functions will help you to handle the sample imbalance and noisy data, right? And whereas the least square is the one which is commonly used, which will not be able to get the better performance when you have a high overlap between them. Cross entropy is better. It can handle to some extent imbalance, but if your samples are highly imbalanced, it's better to go ahead with either adaptive risk factor based loss function or focal loss. So you have to choose. When you look at an architecture, selection of architecture represents the model capacity. So if you choose an architecture with the fewer neurons, you cannot represent the entire data. It will start underfitting. If you choose higher number of neurons, it is like overfitting. Every sample corresponds to one, and then you fit the training data well, but you may not generalize well. So model architecture is a factor. Choice of activation function is a factor that will affect your capacity. Once you fix a capacity, the learning to find the optimal W depends on your observation samples, how they taken from a distribution space. Is it representing the data very well? Is the number of samples which you are having is representing the entire distribution? If there is an imbalance, again it affects the learnability aspect of it, right? And if there is an overlap between the classes, then it's very difficult to find the decision surface which can separate it, right? That will also affect the convergence and finding the estimated weight closer to the optimal weight. These are the factors one need to choose. And again, loss function. What is the right loss function for that particular problem, right? So you need to understand this is going to affect not just only a shallow neural network, this will also affect deep neural network, okay? So in a summary, we kind of understand various factors affecting generalization performance of the network, okay? Thank you.